This is Team Data Conditionals, and our team members are Adnan Asif, Umaima Rahid, Mariam Rahman, and Batul Ahmed. So the data structure we've chosen is Octrees. Like a binary tree subdivides a one-dimensional space into two segments, an octree subdivides the three-dimensional space into 8 octants, where each octant is represented by a node. As you can see in the image here, we classify the octants into 3 classes: region node, empty node, and point node. Given a 3D volume, an octree can be formed by subdividing it into octants such that if an octant has more than one point, it is subdivided further and is called as an internal or region node. If an octant has 0 points, it is called as an empty node and is not subdivided further. Similarly, if an octant has 1 point only, it is not subdivided further and it is called as the point node. So the process of subdivision is continued until all the octants contain 0 or 1 point or become, we can say, point or empty nodes. So hopefully this gives you some idea of our data structure. To understand it better, let's look at the following visualization. While working with the 3D spaces, Octrees are an efficient choice as they reduce the memory consumption from O of m cube to O of m, where m is the number of leaf nodes. The data structure also proves to be beneficial in terms of time complexity, as its access time for each node is just O of log m, which would be O of m if the data was stored linearly, which means we get to perform find, insert, and search operations on a 3D object in just logarithmic time. The data structure stores one child per voxel, and the siblings are stored in consecutive addresses. In our implementation of Octree, we have kept an attribute of max depth, and that is the maximum level to which our Octree subdivides. The depth of Octree acts as a trade-off with the granularity and resolution of the object. The greater the depth is kept, the greater would be the resolution. But as you'll see, our application does not require us to have greater resolution, as we aren't concerned with small specifics of the object, but largely the volume it acquires. Limiting the maximum depth provides us with sufficient information of the 3D volume and also significantly reduces the space that we're using.
Now, all those new things that you've learned about Octrees, put those aside for a moment and look at this picture with me. It's really blurry, right? But even though it's blurry, I can still see that it's a car. Now look at this picture. This picture is sharper, has more details, has vivid colors. In this picture, I can surely admire all the little details of the car, its wheels, its headlights, which I couldn't in the first picture. But if my purpose was just to identify that the object in the picture is a car, then the first picture was more than enough, because I could easily see in the first picture too, even though it was blurry and had less details, that the object is a car. By which I mean to say that it's not necessary to show all the little details of an object to help us identify which object it is. This is precisely the property that Octree utilizes while compressing 3D objects. An octree does not store all of the vertices of the object, rather it stores only those vertices that it thinks are important for preserving the overall structure and shape of the object. And it discards a lot of blurry to show all the little details of an object to help us identify which object it is. This is precisely the property that Octree utilizes while compressing 3D objects. An octree does not store all of the vertices of the object, rather it stores only those vertices that it thinks are important for preserving the overall structure and shape of the object. and it discards a lot of vertices that contribute to minor little details and do not contribute to the overall structure as much. The comparison with a blurry picture wasn't meant to say that Octrees preserve a distorted or a blurry image of an object. Rather, when we'll actually look at examples of Octree compressions, we'll get to see that the object's overall shape and structure has been more or less left intact, and it'll be hard to distinguish the original object from its compressed version. Now this is what I was talking about earlier. On the screen, you'll see two pictures, or two cars precisely. Both of them have been rendered by us on Blender. One of them uses the car's original vertices when it's being rendered, while the other one is actually the compressed version of it. I'll give you 1 second to ponder over which one do you think is the compressed version and which is the original version. Now let me break the suspense. So the one on the left is the original car, while the one on the right is the one that we rendered to the compressed version obtained through our Octree code. Now look at the numbers below them. So the numbers below them actually represent the number of vertices that are used in representing this picture. So as you can see, in the compressed picture, there are almost about half of the number of vertices in the original one. However, even though the number of vertices is half, almost half, the renders look indistinguishable. And this size of the compressed version is only when we've rendered the Octree to a higher level, to a higher resolution. Imagine as the levels lower down, as the resolution lower down, how better the compression will become. Now, as Mariam had explained, that for forming an octree, we have to recursively divide a cube into smaller and smaller cubes until we reach a region node or a point node. So on the screen is precisely that. This is the recursive division for the car that you saw earlier. And you can see in this that this division is so precise that you can easily see the shape of the car forming from just the region nodes themselves. The code that you see on the screen was used for generating the visualizations you saw earlier. So let me explain this code a little bit. First of all, you can see that we made a child, Oct, of the main Octree class. This Octree class depicts the Octree data structure and all of its functionalities. But at the moment, this child only contains the root node, and as of yet, it does not store any image or 3D object. Then we can see that we have an object, we have a child by the name of car of a parent class object or OBJ. This class deals with our input files, which are object files of 3D objects, and helps us to also store those object files into Octrees, like we've done in the next step by storing the object file in car to the child Oct. The class Octree has two functions, level points and get Octree regions, to get back the vertices and regions of the Octree at a certain level. So this is precisely what we've done. We've extracted the vertices and the regions from the Octree by using those functions. Now comes the fun part, where we get to see our Octree in action. Now, as I told you earlier, we've used Blender for rendering our Python scripts. So display is precisely a function which creates a mesh in the Blender environment using the list of vertices, edges, or faces passed to it. So passing the vertices that we obtained earlier to the display function will give us the compressed version of the card that we saw in the very start. For generating the regions, we first had to extract the regions, vertices and faces. So for that, we made another helper function. And now that we had our regions, vertices and faces, we could easily pass those lists to the display function so that it could render a mesh out of them and give us the output that we saw just before the slide.
Imagine you're walking down the street and this is your first person POV. What I want you to do is to think about how you make decisions when we are moving. So, what if you wanted to move ahead of this lady right in front of you? How would one do that? So, what our brains would normally do is that detect that there are these two empty spaces in front of me, so one on the left and one on the right, and move in one of these spaces. Okay, so these two spaces are represented by these two rectangles over here. So now I want you to think about what our brain did. So we analyzed that, okay, there is this enough space for us right in front of us, so there are these two regions and we can move in one of them. So think about it, we could have taken multiple approaches, such as we could have just looked at one point at a time or one step at a time instead of considering these two large spaces. But we didn't, because we know that this is the best possible way. So this is quite similar to our application, or I should say the approach we propose, which is to plan an optimal path in a real 3D space, which can be used in open world 3D games or by autonomous machines who are working in remote environments. Now you might be wondering, what does this all have to do with Octrees? So for this, what I need you to understand is that Octrees aren't just used for storing 3D data or compressing it. Although some people might think that this is their only purpose, but they provide us a lot more information about the 3D environment, which can be utilized for several applications. Which in our case, we are using it for an optimal path planning approach in 3D spaces. So our Octree isn't just compressing the 3D map for us, but it is also providing us the information about all the empty regions in our space so that we can move freely. So what we propose is an approach to find shortest path in a 3D environment. Now this is a problem that has been overlooked in computer science for quite a while and has been given attention lately because of the rise in popularity of autonomous drones and autonomous vehicles, and especially the popularity of open world 3D games. But most of the approaches available are rather just in theory, or they use very high end algorithms and hardware. So, this is a problem that we aim to solve. First of all, we need to compress a map using an Octree. So, for this, we made a map in Blender and then we stored it in our Octree, and I don't think that I need to explain furthermore that how this compression is done. We have explained it a lot. So for the time complexity of this operation, it takes n log n time to store all the data in an Octree. So order of n times to traverse over the list of vertices and log n time to store each data point in the Octree. So okay, so moving ahead, we have okay, so now we want all the empty regions in our map. So for this, what we do is that when we are loading our map in our Octree, we know we store all the point nodes and the information of all the region nodes. But then all the nodes that are left are empty, which means that they are the placeholders for our empty regions. So we can traverse over our Octree and then we can calculate the values for at which that empty node resides. So by this we can get a list of all the empty regions in our map. Okay, so now for the third step, what we need to do is we need to calculate all the neighboring nodes of an empty region which are available and that are also empty. So now this is a very tricky step because we don't are all of our empty regions are not of the same size. So if an empty region is like really big, and so it can be surrounded by a lot of small empty regions, there it would have a lot of neighbors, and we can't really calculate how many neighbors a single empty node has. So for this we had to go for a force approach, but we came up with a formula that would allow us to compare the centers of both the neighboring nodes, and then we can figure out if they are neighboring or not, if they are neighbors or not. And then using an empty region and all of its neighboring regions, we create a graph. So this step would have complexity of order of k square, where k is the number of empty regions. So now for the last step, all we need to do is use a pathfinding algorithm. So for this one, we are using a variation of Dijkstra algorithm, which would work in 3D spaces, so such that it would calculate all the weights and distances in 3 dimensions. And yeah, we are also using Dijkstra because it gives the optimal path, which is the shortest path from one point to another. So yeah, now let's see the results. Okay, so as you can see that our algorithm was able to find the shortest path between these two nodes, but one problem is that we haven't specified any size of which our machine is. So it's right now it is also going under the car, which right now is optimal path for it. And these boxes represent all the empty regions it is going through. So as you can see that we were uh, successful in finding optimal path between 2 points in a 3D space through this approach.
So now let's talk about the pros of our approach. As we have already discussed, our approach results in better memory management because of the compression of the 3D image through the Octree structure. It also leads to fast access of data as the data is stored in regions instead of points. So the nodes of the tree are reduced because of that, and since it's a tree, the time complexity is already logarithmic. And the tree has 8 nodes here, so the time complexity basically becomes log base 8. Other than that, our approach enables us to render a specific region instead of the entire octree. For example, if we use Octree for the area map in a 3D game, we can render a specific path within the reach of the player instead of the entire area in the game itself. Next, we say that since our approach uses Octree to work on regions instead of points, I mean, through our structure, we get regions which are mostly a big group of points. So, going from one empty region to another instead of traversing through points saves time and computing. We can also say that our approach can be cost efficient for 3D path planning for navigating machines such as drones, etc. As as the path planning for the machines would be easier when it has to navigate from one empty region to another instead of calculating if every next point it has to move to is empty or not. It just has to see if there is an empty region next to it and it can go through it without any hurdle in the way. This reduces our need for complex mechanisms and huge computing power, which basically saves us from using expensive hardware. Next, we discuss some points through which we can better approach. Here are a few things that we came up with. So, as we have seen that an octree results in nodes that are basically different sizes of regions. So, after getting these nodes through our octree, we have used a brute force approach to come up with a graph of empty neighboring regions. We think this can be improved and done in a more precise way to make our approach a little bit more efficient. Other than that, we use an elevated Dijkstra algorithm to navigate through empty regions in 3D, which basically means we check all neighboring nodes to get to the nearest. Here we think using an even advanced algorithm such as A star can result in less time consumption and more efficient traversing, as it tries to look for a better path by using a heuristic function, which gives priority to nodes that are supposed to be better in some way based on some factors. This algorithm is basically said to have brains. Also, for now, our approach is for point navigation. I mean, right now we have not specifically designed it for a particular machine. So for now, it can take a path from below the car as well. When in actuality, generally the machines aren't small enough to do that, right? So when we customize our algorithm for a specific machine, we will have to alter the algorithm and factor in the size of the machine itself to basically make it find big enough regions for our machine to navigate through.
This is a GitHub repository which contains all of the code as well as the object files that we used.
Well, here are the references of the sites that we have referred to, and that is it from our side. If you have any questions, feel free to ask. We'll be happy to answer. Thank you.